Okay, so let me remind you what we did up to now. So the first part was the definition of arithmetic intersection degrees. That means that real numbers of the form arithmetic degree of products of so our first arithmetic chain classes of Hermitian line models. On some proper flat scheme over spec Z, and Z is a d-dimensional cycle on X. Part 2 was an application of that to the height of a variety or of a cycle. Something of the form height with respect of an Hermitian line model L bar of some say irreducible d-dimensional closed subscheme to be defined as the arithmetic degree of C1 hat of L bar to the power D against Z divided by the D plus 1. No, sorry, D. And geometric, so then, sorry, D should be the dimension of ZQ, so here it's D plus 1, and the degree of C1 of L to the D on Z. And I have given examples. For example, the Néron-Tate height in the good reduction case. And then in order to be able to have more examples, interesting heights given by this formalism, I started to explain the theory of adelic metrics. And then there was a part 4 which was missing, and a part 5 about semi-positive adelic metrics and existence of generalized arithmetic intersection degrees. So the idea is when L1, LD are vector model, this line model on X, but on X will be something on Q, and L1, LD line models on X plus semi-positive adelic matrix. Then there is a number of the form arithmetic degree of, we'll start at L0, L0 bar, C1 hat of LG bar against Z, where Z is in XQ in X, a d-dimensional. Okay, and I just remind you that the definition of this number follows that one. So I take limit, I take algebraic metrics on these line models that approach semi-positive algebraic metrics that approach the given adelic matrix. And I compute this the same arithmetic intersection degree now on the corresponding models, and I take for Z the Zariski closure of this Z will be the Zariski closure of that Z on the model. So I can use the definitions of part 1 to compute analogous intersection numbers, and there was a proposition that proved that when the matrix approach the given adelic matrix, these numbers converge to some well-defined real numbers, which I denote by this. Okay, and thanks to this, there is a new. There are more examples. For example, from algebraic dynamics, when f from x to x and when this is polarized algebraic dynamics, so there is a line model L on x, which when pulled back by the finite flat morphism f, when finite, becomes a power of itself. And I've proven that there is a unique adelic metric if Q is greater than 2 that turns this given isomorphism into an isometry. And so in some sense that's a canonical adelic metric. And it is semi-positive if L is ample, for example. And as a particular case of this, you have the case of Néron-Tate heights. Again, but this time without any hypothesis of good reduction, because this process works on the generic fiber and computes adelic metrics. And so this shows that this way of defining the Néron-Tate height is Tate's way of defining Néron-Tate's height. So if you the whole history of Néron-Tate height in the 60s, it was understood that the height was approximately bilinear, and independently, Néron-Tate gave two constructions of bilinear forms or quadratic forms that are that differ from the Néron-Tate height from a bounded amount. And there is so the one strategy due to Néron is to define at all places very quantities that behave in a very precise way. And this construction is the generalization in some sense of what I did in the first part, and understanding that when there is good reduction, it's quite clear to do what to do. But when there is bad reduction, it's more complicated. But then there came John Tate, and he showed via a very simple limit process that one could define the Néron-Tate height as a quadratic form very easily. Just take the height, take any height function in any sense, which has no correct property. Take a height of x, and this should be close to a quadratic form in x. But then to define this quadratic form, just take height of n times x and divide by n2 and let n goes to infinity. And Tate proved that it converged to some well-defined number which gives a quadratic form. Okay, so this is this limit process, and this limit process we have seen its role in the theory of adelic metrics. Because this canonical matrix I define via the Picard fixed point theorem, whose proof involves the limit process of iterating the dynamical system. So, and that's the point at which we are now. I have also defined admissible adelic matrix as a quotient of to semi-positive adelic metrics. So now the goal is to talk about equidistribution. So next part is defining measures on those spaces. So definition. I remind you that for every place V, I have this analytic space xvn, and I had defined the adelic space to be the disjoint union of all these xvn. And well, I said that phi, a function on this adelic space is admissible if the metric is the adelic metric. So on OX and not given by norm of 1 is exponential minus phi is admissible. So at this point, you maybe understand why I switched from Zhang's terminology to another one, except that Zhang's defined also admissible stuff in some other paper. But because here he says that this metric is called integrable in the sense of Zhang, and I don't want to say that this function is integrable if the corresponding metric is integrable. So that's a precise reason why I have another terminology. And yeah. S, okay, S is a set of places of Q, so it's 2, 3, 4, no, 5, 7, infinity. Okay, and of course there is a similar definition if I take one function phi v on xvn, and I will say that phi v is admissible if when completed by 0, it's admissible. So it's the v-adic metric. I allow myself to talk about a v-adic admissible metric. And so there is one important proposition, which is due to Gubler, is that admissible functions, so maybe C adm is dense in CC of, maybe I could write admissible there. So density of admissible functions in all functions. And this result is a combination of the existence of algebraic metrics on OX which distinguish points of xvn. So I mean, when I have 2 points in xvn, 2 distinct points, there is an algebraic metric that gives to one different values at those 2 points. And then the fact that algebraic metrics are stable on the sup and inf. So the formula, one can check that the supremum of 2 algebraic metrics is again an algebraic metric, and the infimum as well. And so an application of Stone's theorem. Which is sometimes called Stone-Weierstrass, but we're far from Weierstrass' point of view, because these are two density theorems for functions, and one is for algebras separating points, and and the other is for not algebras but lattices, so subspaces of functions stable by sup and inf, and separating functions. So it's rather stone. Where are my notes? Over there. Okay. So maybe just little stuff. So if I'm looking at what does this statement mean? If I'm looking at one finite place only, it means that if I give myself any continuous function on xvn, then it's a uniform limit of any continuous function on xvn, which is compact. So it's a uniform limit of admissible functions. And if I take something in this CC of x hat R, and x hat is not compact, that's a disjoint union of infinitely many objects, it means that any function there has to vanish at almost all places, and at the remaining places, it's a limit of algebraic metrics, and which are 0, which gives 0. So that's a definition of the topology of the inductive topology, this topology of compact on the space of continuous functions with compact support. And so now, when I apply this, the existence, what does this theory give? When the line bundles N1, LG bar are fixed, but here I take the trivial line bundle with some metric. It shows that there exists, so V is a place of S, and Z will be an integral closed subscheme of dimension D, and L1 bar, LG bar line models plus admissible metric. Then there exists a unique measure on xvn, denoted by C1 of L1 bar, C1 of LG bar, delta Z, such that the arithmetic degree of this time OX plus the metric, so I should have given the definition, OX of phi, so this will be OX of phi. So C1 hat of that, C1 hat of L1 bar, C1 hat of LG bar, again Z, is the integral of phi so the integral of phi, this function phi, against this measure, with this fancy notation, with very many letters for single stuff, will be the arithmetic degree of this admissible metrized line bundles against those admissible metrized line bundles and Z. For every phi in C ad xv for any admissible function phi. Or maybe I should write phi v, but. And the second part is this measure is supported by ZVN. So the analytic space of the what do you say? Why do I write phi v? Okay, well, I say. Okay, and its total mass is the degree of C1 L1, C1 LG, on Z, so the geometric degree. And if L1 bar, LD bar are semi-positive, then this measure is positive. Well, and I don't write it, but of course, this pairing is multilinear in L1 bar, LG bar, and multilinear and symmetric. So this measure will be multilinear and symmetric. So let's write it. C1 of L1 bar delta Z is symmetric and D-linear in L1 bar, LG bar. Okay. So essentially, there's not much to prove now. Is that in fact, by linearity, we assume that L1 bar, LG bar are semi-positive. And then we look at the inequalities of last week. Well, not last week, last lecture. And in that case, you observe that if you take for phi a positive function, the corresponding arithmetic degree is non-negative. So that gives you on algebraic matrix or on admissible matrix a linear form, which is positive. And so it has to extend uniquely to the closure of the space, which is that space. So you get a positive linear form on the space of compactly supported functions. That is a measure. So you get just a measure by density and from the previous work. And then you observe all those properties. So one remark, if V is Archimedean, then this so then C1 of L1 bar, etc., all these objects can be viewed as a positive closed 1-1 currents on XV_n. Well, maybe let's write X of C. And let's forget that I have mod out by complex conjugation. And these currents are defined locally as DDC of the logarithm, DDC of a continuous PSH function. And so there is a theory due to Bedford Taylor and de Mailly allows to multiply these currents. And the point is, in general, you don't have the right to multiply currents. Currents are objects which are differential forms with coefficients in distributions, and you don't have the right to multiply distributions in general, so you don't have the right to multiply currents. But in this case, the property that these currents are locally DDC of a continuous PSH function allows you to define this product. And the definition by, well, maybe it's not the definition, but one way in this case but there is an important theorem by both group of authors that this multiplication will be continuous. And so when when a smooth PSH function will approach your continuous PSH function, the corresponding currents here and there, which become smooth forms approaching currents, will be approached, and the product of the smooth forms will approach the product of currents. And so that shows that this limit process that I have done 2 days ago is exactly the same at the Archimedean place as in Bedford-Taylor domain. And so, and the definition is compatible. So that's the first remark. And so in the case of the finite Archimedean place, and so now let's take the case of a finite place. Then, so this definition of a measure was given in a paper of mine, so published in 2006, but without knowing what C1 of L1 bar is. So I have written a long name for a single object, and at that time I had no clue at all about what C1 of L1 bar, C1 of LG bar could be. But there is an ongoing project by Antoine Ducrot and myself. So in with Ducrot, we found a correct definition of differential forms and currents on XVN, and the analogy becomes complete. So, and this measure is the product of currents. So C1 of L bar, C1 of LG bar, and in fact, this is I take on Z, and I push. So I take currents on Z, I make the multiplication on Z, and push to X. Yes?
Do you have a definition for positivity of subscribe?
Yeah. Yes, because that in the first version of our paper we didn't prove that, but so we had another definition of semi-positive, which in principle could be different. But I think it has been checked by Gubler and Kuhneman and maybe Martin as well in this group from Regensburg that all definitions coincide. Actually, it was not clear in Zhang that if you took an algebraic metric that was semi-positive and an analytic metric, it was already semi-positive as an algebraic metric, which had something to do with degrees on vertical curves. So they checked everything like that. So then I will give 2 examples. The first one will be take Px to be Pn, and line model will be O of 1 plus the veil metric. So the veil metric is just given by the max, the usual formula, but at the denominators you don't put like in Fubini study, but you put max of coordinates at all places. So the norm of a section P at a point of homogeneous coordinate x0, xn will be absolute value of the polynomial P, the adic absolute value of P, divided by maximum of P and to the power degree of P. And then what are the measures on the measure C1 of L bar delta Z. No, not the delta Z. C1 of L bar to the n. I will give two different formulas according to V being finite or infinite. So if V is infinite, then inside Pn, so in Pn of C, you have C to the n, just compactify as you wish, as you imagine. Inside C to the n, you have C star n, and inside C star n, you have the circle to the power n, which corresponds to points whose all of whose homogeneous coordinates have the same value. Okay, so that's a circle of dimension n, and this is a Haar measure, the normalized Haar measure on PNCs, and on S1n, which is a subset of PNC, if it's finite, is infinite, sorry. And if V is finite, this will just be some Dirac measure at a single point of and so psi V is a point of xVn. So xVn is PNV, and it is a Gauss point. So maybe I had explained, not explained, but just recall that there was a specialization map from the Berkovich space to the scheme of the special fiber when I had a model. So if you take for a model Pn over Z, or Pn over the Pn over Qp, then I have a specialization map from PNV n to the scheme Pn over the special fiber. And the fact is that the generic point of the special fiber has a unique preimage under this specialization map. And this preimage is the Gauss point. So this case is quite a singular case, because you see that here the measure is it's supported at a single point. Here it's supported on an object which is smooth. It's a product of circles, but anyway, it has a close support, a very small support in PNC. Not so small actually, but the other example, if X is an Abelian variety, well, let's say over Q, just to simplify a little bit. So then C1 of L bar to the n, so dimension of x n. This will be the Haar measure on x of C with mass degree of L with respect to x. So if V is infinite, that's really a smooth measure on the space. And if V is finite, then there are two cases. The first case is a case of good reduction, or maybe potential good reduction. Then the measure C1 of L bar will just be some Dirac some Dirac measure at a single point. So psi v is an analog of the Gauss point. In the case, and well, there are not only two cases, but there is a chain of cases. But the two extreme cases are good reduction, and the extreme case is totally degenerate reduction. And this case corresponds to the, for example, to Tate's elliptic curve. So in this case, which is defined usually at Cp star divided by Q to the Z, where Q is some element of Cp of absolute value strictly smaller than 1. So those are cases where the analytic Abelian varieties can be written as a quotient of a group by a lattice. But it's not the same group. It's not C to the n divided by a lattice of rank 2n. It's C star to the n divided by a lattice of rank n in C star to the n. And in some sense, that's half of the uniformization. Because when you have an elliptic curve with period lattice 1 generated by 1 and tau, you can first say that the quotient is, you just mod out by the 1, so by z. And then when you mod out C by z, using the exponential 2 pi I function, you get C star. So it's C star divided by exponential 2 pi I tau, and the group of that. So in some sense, this result shows that elliptic curve with bad reduction have a partial uniformization, as in complex case. And then, so in this case, from the analytic point of view, is GMN divided by a lattice lambda, and GMN and the multiplicative group, the analytic multiplicative group divided by some lattice in general. And inside GMNN, there is not only one Gauss point that correspond to absolute value of psi is 1 in some sense, but you have Gauss points that correspond to absolute value of x1 is R1, absolute value of xn is Rn. And so inside of this, you have something which is called a skeleton of GMN, which is canonically isomorphic to R to the n. So in the case of GM1, that you have a real line, and you will mod out this real line by some analog of Q to the Z, where Q is of absolute value smaller than 1. So what you get is a product gets one gets a product of circles. So which will be the skeleton of XVN. Which will be isomorphic to R mod Z to the n. And C1 of L bar to the n is the Haar measure on this skeleton, normalized by the degree of time log of x. So that shows that for Abelian varieties, or for elliptic curves, you have two cases. Either the measure is concentrated at a single point, or you have bad reduction, and then inside the analytic, the Berkovich space of the elliptic curve, you see visually a circle and the measure I had defined is the Haar measure on this circle. Okay, and the general case is due to Gubler. I mean, this result is due to Gubler, and there is for Abelian varieties you have intermediate cases that is part of the Abelian variety in some sense can have good reduction, and then you get a mixture of those two cases. Good. J'ai 1h30 aujourd'hui. So the next goal is to so now is to go back to global properties, and so the next section set, is about volumes, and so I will describe the relation between the arithmetic Hilbert-Samuel theorem, that was the object of White-Chen's lectures, and the properties of height. And in section 8, I think I will discuss equidistribution and maybe prove the equidistribution theorem of Yuan. I mean, proving it by assuming many properties, but explaining this. So let's take my notes. I'm surprised because what I was what I was going to write is wrong, so I have to change this. So let's go back to algebraic matrix for the moment. So we take X and L bar. And now I will assume that L is semi-positive, and L bar is semi-positive, and I will also assume that LQ is ample. And then it's interesting to look at the Riemann-Roch spaces of X inside XLQ LQ. So this is a finite dimensional vector space. And inside this, I have the space of maybe Arakelov sections, which will be the intersection of the space of integral sections, such that the norm of S at the Archimedean place is smaller than 1. Okay, and it was the insight of Arakelov to consider the logarithm of the cardinality of this set as the analog of the dimension of a similar vector space when you have a fibration of varieties over curves. Now imagine you take S and S non-zero in H0 hat of XL bar. and take a point x in x, a close point. And we can compute the height of x with respect to the line model n bar. And the definition of this is just 1 divided, say, by the cardinality of the degree of the residue field, q of x, kappa of x, or q, of the arithmetic degree of the, you remember this, where epsilon x, which will be, so f will be kappa of x, this will be this morphism. And now if you want to compute that, remember we take a section, in the definition of this arithmetic degree, we take a section that is generically non-zero at the, so we can take, if s of x is non-zero, we can take s on x to compute the arithmetic degree. And so this gives, so 1 divided by the degree, and something like the logarithm, so some term which is positive at finite places, because the section is integral, because it's because s is in, and plus sum over all, integral over, say, x of c, all conjugates of x, of log norm de s minus 1. And this is non-negative because this is non-negative because the section is assumed to have supremum norm greater than 1. So this is always positive. So this is height positive. So we see on this example that if the line model L bar L has section which do not, which are integral and of subnorm smaller than 1, then the height of almost all points is negative. I say almost all because if a point x that satisfies s of x equals 0, if it lies on the divisor of x of s, I cannot say anything. But outside of this divisor, the height is bounded from below, and not from below by anything, but from below by 0. So this argument can be generalized. I can replace L bar by some I can consider powers of L bar. And now when n, maybe not n because n is usually the dimension, but okay. So well, okay. So now the interest of taking powers is that the dimension h0 xq lq to the k will grow polynomially in k. It will be the dimension will be a polynomial of degree. Say d is dimension of x. What's that? So I could write n. It will be a polynomial of degree d in k. So there will be a lot of integral sections, and a lot of sections there, and possibly many more sections there, except that we don't know whether there are or not. But so there is a definition of the volume of x, say fq, lq, which is the limit sup of h0 of xq lq to the k divided by k to the d divided by factorial d. So this is the usual algebraic volume, and it was classically defined as a supremum limit, but in fact, because of Fujita's approximation theorem or because of the theory of Ogunkov's body, whatever, it's now known that this supremum limit is the limit. So you have a volume. And there is a similar definition of the arithmetic volume of X with respect to L bar, which also defined as a supremum limit of H0 at X Lk divided by K, this time d plus 1 divided by factorial d plus 1. And what this argument shows is that if the arithmetic volume of X L bar is say strictly positive, then well, let's say it's the negative. Then there exists some positive real number epsilon, and a closed subset Z in X and distinct, such that the height of X is greater than minus epsilon for all. No, it's better to write this. If it's positive, then there exists that, so that the height of, for all X in capital X minus Z. Because if this arithmetic volume is strictly positive, there must exist, this number must be eventually non-zero. And so I take a section of L to the k. Here, maybe I need a bar. I play this game with L bar to the k. And outside of the divisor of this section, the height will be negative. Okay? And so the question is, it's unlikely that this volume will be positive always. This is the case when the L bar is in algebraic geometry. When the volume is positive, you say that the line model is big. So this is an analog of an arithmetic big line model. And this is natural definition of an arithmetic big line model. And there is no reason a priori for which your given line model would be arithmetically big. So it is so the volume is something, and you want to know what you can say according to the volume. Okay. So now what you have to do to make the volume positive, the idea is that you need you want more sections of norms smaller than 1. So what you do is at the Archimedean place, you divide the metric by something and make the metric smaller, so you make the volume grow. And you have to understand the difference between this space H0 hat of L bar and the new space is the original space and the new space where the metric is smaller. And the comparison between the number of sections of norms smaller than 1. So then there is a paper by Gillet and Soulet. I think it's in the Israel Journal of Math in '86. That showed that if you take, you multiply L bar, you switch L bar and you multiply metric by lambda say smaller than 1 at the Archimedean place, and that maybe not a lambda smaller than 1, and that shows that the volume. So it will be. I should write that by exponential. So L bar the lambda, and from the result you can have something about the volume of L bar the lambda, which will be exactly the volume of X L bar. And then I should not plus d plus 1 lambda volume of XQ LQ. So when you multiply the metric by lambda, you shift the arithmetic volume by lambda multiplied by the geometry volume, and d plus 1, which is always there. Okay? So, it's too bad I erased this stuff here. So I should say that there is an alternative definition of the volume, which is weaker but easier to manipulate, and which is called volume index chi of XL bar, and which relies on something of some h0 hat index chi. And the definition of h0 hat index chi is that you take this h0 xl. Now you take this, and this will just be a Z modulo finite type. Torsion free. It's really a lattice. And on this, you have the supremum norm. So you have a lattice plus a norm at the Archimedean place. And from that object, you can define so which will be chi of this, and this is defined as the logarithm of so you tensor with R and you divide by the lattice, so that the covolume of the lattice in the real space of sections, and you divide by the volume of the unit norm, of the unit ball. And when you do this, maybe there is a -1. This is, yeah. And when you do this, the choices of volumes here and there, which are supposed to be defined by the same measures, does not have any importance. This depends on the choice of a measure. Here you take another one, you take the same one, and then the quotient, the ratio is well defined. And so it gives you another number. And the theorem of Minkowski tells you that usually Minkowski says that if this is so if the covolume of the lattice is small, then there are sections of small norm. So in fact, you get something, but I'm sure I'm not written the correct. Apparently, it's okay like this. I'm surprised. I've written this in equality, but maybe there is some. I don't remember whether there is another error term or not. I'm not checked. Do you know, Pascal? There should be an error term. Yeah, something. But the error term at the end does not make any importance, because when you pass to infinity, when you take powers of k, and then you will have an error term divided by something, and the terms corresponding to error terms will go to 0. So what is important is that the arithmetic volume is greater than the chi volume. And here there are hats. Okay. And so that's so just to give bibliographic references, up to in the literature on this topic, up to the paper of Yuan, essentially only this volume, the chi volume, was studied. Essentially, that was the one that was classically studied in the literature. But then, after Yuan's paper, there has been a lot of work by Yuan, by Chen, by Mouraki. Well, essentially, that's it. And they put forward that we really studied this volume. That is, whose analogy is closer to the Arakelov philosophy and so on. And so then all these results, for the result of Jessoule is older, but the emphasis has been put on this new volume. But for the applications, it's enough to use the chi volume. So anyway. So now there is the arithmetic Hilbert-Samuel. Oh, sorry. Exactly. Yeah. So before I state arithmetic Hilbert-Samuel, I should say that if you apply this here, but now to the arithmetic volume, if we say that if the arithmetic volume is greater than lambda, then the point will be bounded from below by something which is the ratio of the arithmetic volume and the geometric volume. So what is the formula I should write? Is that so the corollary of this is that if so assume that LQ is big, that is the geometric volume is non-zero, then for every t smaller than the ratio of the arithmetic volume divided by d plus 1, the geometric volume, the set of points of height smaller than t is not dense. In X. It's not Zariski dense. So that's exactly the combination of this statement and that statement. And the result that appeared in the literature usually, and that was used, that will be sufficient, is the same for Volkai. Okay. Usually people were writing this, but since the Volkai is smaller than the Vol, the statement with the chi is weaker than the, so the statement with chi is usually it was with Volkai is exactly it's an inequality, maybe not due to Zhang, but because that's a straightforward corollary of the arithmetic Hilbert-Samuel theorem, but Zhang has really showed his importance, its importance in the field. Okay, so that's the role of volumes. And so now I need to quote the arithmetic and that says that if so LQ is big, L bar semi-positive, I'm sure I should say big or ample. No, it's enough to assume that L bar is semi-positive. Okay. Then what happens is the fact that the arithmetic, no, say, assume LQ is big. Then the Volkai of XL bar equals the arithmetic volume. Two arithmetic volumes are equal, in fact. And they are equal to something which is just the height of, no, which is not the height, which is just the arithmetic degree of C1 hat of L bar to the power d plus 1 against x. So what is important is not only the equality, but that we have a precise formula in terms of arithmetic intersection theory. And that is the log of the fact that if L is nef and big, then the volume of LQ, sorry, is nef and big. Then the volume of XQ, LQ, okay, is a degree so the leading term of the Hilbert-Samuel polynomial in the big and nef case is exactly the degree divided by plus the factorial. Okay, so the arithmetic Hilbert-Samuel theorem is a counterpart of this formula for the Hilbert-Samuel polynomial. Okay. So now I will just say that as a fact, maybe it's hard to define the intermediate, for example, to have analogs of this Minkowski result or and so on. But now when I will take a line bundle with a semi-positive adelic metric, and I will take algebraic metrics converging to this, I will have analogs. The arithmetic volumes will converge to the volume plus error terms, but everything will match. So I will use these results. This is also true for so this extends to adelic metrics. I mean, the computation, what extends is complicated. This extends to at least. So the theorem that outside, if I approach adelic metrics by algebraic metrics, I have theorems, and everything will converge. So I have a combination. So maybe I should try the theorems. It should be better. So the consequence is, and my notes for the moment are totally wrong of that, so take care. So assume that L bar is a semi-positive adelic metric on L metrized line bundle. So I have X, L, I assume that LQ is big. And for every t smaller than C1 hat of L bar to the d plus 1 on X divided by d plus 1 degree of C1 of L Q, C1 of L to the d on X, the set of algebraic point of height what did I write? yeah, okay, of height smaller than t is not Zariski dense. Okay? So that's the statement. So this result is proved from the other one just by approximation. Okay, so now, I should give references. So this theorem, all these theorems are proved by a lot of people. So this theorem, the first proof is due to Gilles-Soulet using an analytic estimate of Bismuth and Vassereau. And then there has been a more elementary proof by Abbes and Bush. And I think that's it. And for the other stuff about arithmetic volumes, so the names to quote are Yuan, Chen, and Moriwaki, according to the generality of the treatment. So now, I have 10 minutes to explain distribution. But fortunately, that's very easy. So first of all, we fix a place V. And so now, if I have X a closed point on X, I will define a probability measure delta of X on XVN, which will essentially be given by, you see, XVN. Remember that it contains X of CV modulo Galois. So I can take this point, which will be I can take all the conjugates of this point, and they will make finitely many V-adic Galois bits, and so supported by the Galois orbit of X, maybe of any. Maybe, let's say of X. That, so let's say that it does not really make sense, but so let's say X hat, which is a point in X of CV, going to, and here that's Galois of CV sur QV, and I will take the Galois of CV over Q orbit. If I wish, I can take Galois of CV over a finite field, but a finite extension, but it's not important. Okay, so that's the definition of this probability measure. So for example, if you take on the line, you have the affine line of the projective line over Q, and you have the point I and minus I, the closed point corresponding to I and minus I. The measure I will put on the projective line over C will be 1/2 of the Dirac measure at I plus Dirac measure at minus I. And in fact, I have mod out P1C by the complex conjugation. So at the end, that will make the Dirac mass at this Galois orbit. But essentially, that's the measure. And so now two definitions. If Xn a sequence of closed points in X, I will say that Xn is generic if Xn converges to the generic point of X. That's a funny definition because the Zariski topology on schemes is not separated. It's not Hausdorff, so people are not used to talk about limits in such spaces. So what does it mean? It's maybe better to write down the definition. It means that for every z strictly smaller in x, and x is assumed to be reducible here, the set of n such that x is in Z is finite. Xn is up to a certain point, your points do not belong to any given Zariski closed subset. So that's the first definition. And the second definition is that Xn is small with respect to some L bar if the height of the point Xn converges to the number of lost, which is no more on the blackboard, which will be converges. Yes, you said that height h of and so here L bar is some L bar is a line model with a semi-positive matrix. And if you see this, you look at this, you observe that if you take this point Xn and you apply this theorem for this Xn, you see that necessarily for n large enough, the points won't leave, the heights will be strictly greater than t. So it means that in any sequence of points, the height is ultimately greater than anything smaller than this, which is the height of x. So that in any case, the limit of those points cannot be smaller than that. There may be no limit, but if there is a limit, it must be greater than that, or the infimum limit is greater than that. Okay? And so now the goal of equidistribution is to say what happens when we have both properties, so generic and small, and necessarily something will happen. When you have an inequality which is forced, and you take points that achieve the equality, usually in calculus of variations, you know that there is some vanishing first differential. And so the idea of equidistribution is to look at this vanishing of differential. And so the theorem of U1, but which follows a former result of Szpiro Ullmo and Zhang at Archimedean places, and in Yuan there is something at all places, and it follows a very weak version of that I proved for the case of curves. In fact, Autissier had also proved something for curves in this strategy. Is that if so L bar is semi-positive, and so if the sequence Xn is generic and small, then the sequence delta of Xn converges to the measure C1 of L bar to the n divided by degree of C1 of L, so degree of x with respect to L. I have to get a positive probability measure, probability measure on the space. Okay, so this is the theorem of U1. And maybe I'll just explain, because that's cool. The clock doesn't turn so fast. So proof in the case of Szpiro, Ullmo, and Zhang. Because that's where we understand the strategy of the proof, and then I give the additional input that Johan had to prove and explain the. So the proof in this case is that in the case, so V is the Archimedean place, and L bar, the metric. So the hypothesis is that, and the metric, Archimedean metric, so the curvature form at infinity is strictly positive. Yeah. LQ is big. Well, maybe also don't mind. I think big is enough, but yeah, big is enough, I think. Well, okay, in any case. So the hypothesis is that at infinity, the curvature form is strictly positive. And in that case, X was smooth. So then the idea is we will apply the variational, the inequality of Zhang, not only to L bar, but to twists of L bar and to small twists. And look at what happens. So the idea is apply. So Zhang's inequality is that the infimum limit of the height of the point is greater than the height of the variety. And so apply it to H L bar of, to not to L bar only, but to L bar of epsilon F. Or maybe L bar of F. Well, F is a function on so F is a smooth function on X of C. But what is the curvature of C1 L bar? Is of F. This will be C1 of L bar plus DDCF. And this is strictly positive, and this is whatever it can. And maybe the sum is not positive, and so maybe this curvature form is not semi-positive. And I need to know, to apply this inequality, that L bar is positive, semi-positive. So the idea is that if you multiply F by some small enough real number, then this will be semi-positive for epsilon small enough. I know I put back my epsilon, which is positive for epsilon small enough. So now we know that what this is. That's a quotient of two terms. The denominator is just a degree, it doesn't move. And the numerator is some arithmetic intersection number, is C1 hat of L bar of epsilon F to the power d plus 1 on X, divided by something. And now I use multilinearity to compute that, and to compute the expansion of that along the powers of the epsilon. So here I have C1 bar of L bar to the d plus 1 on X. That's the leading term. And then the next term is epsilon times d plus 1. And then it's exactly integral of, if you look at what happens, is integral of F against C1 of L bar to the d, and then plus bco of epsilon 2. Then the rest I ignore. And divided by whatever it can. And so the first term is just what it is for n equals 0. So exactly HL bar of x. And the second term is exactly epsilon integral of f against the measure C1 of L bar to the D divided by degree of L. And that's the result of this right-hand side. And now for this, I have infimum limit of the height. And here, if you compute the height of xn with respect to the line model L bar of epsilon f, you get exactly the height of xn plus epsilon times the integral of f against this measure, just because of the way the height is computed. You use the same section to compute the height if you prefer, and at fine places that does not change the formula, and the Archimedean place, it shifts the formula by this term. And so now what is this? This goes to the height of x. So at the end, you get that infimum limit of epsilon integral of f delta of xn is greater than epsilon integral of f C1 of L bar D divided by the degree plus bco of epsilon 2. And now you just let epsilon goes to 0. So when epsilon goes to 0, but epsilon is positive, when you divide by epsilon, you will keep the inequality. So you get the infimum limit of integral of f delta of xn is greater than that. And if you make epsilon negative, then you divide by epsilon, but you have to change the inequality. So the limit inf becomes a lim sup. And you are smaller than okay, so you have shown that the lim sup of the lim sup is smaller than something, and the lim inf is greater than the same thing. It shows that the lim sup equals the lim inf equals the limit. And so this proves the this proves the equidistribution theorem of Szpiro, Ullmo, and Zhang. And for Yuan, it's more complicated. And he proves an arithmetic analog of a geometric inequality of Xu that has said that if L and M are M-pole on X, then the volume of L minus M, so X and say L tensor L minus 1, it's greater than the volume of XL minus d it's greater than that. Just remember that if this is ample, then the volume is just C1 of L minus C1 of M to the power D on X. And you can just expand this by multilinearity. And the first term you get is that, and the second term you get is this one. And so it's sure that at least in any case, even if L minus 1 M is not ample, then the volume is greater than 0. So what Yuan proves is an arithmetic inequality of that. So basically putting hat all over the place. And this inequality shows that you'll be able to make this small deformation because M will play the role of the small deformation. But I think I do not want to say more about this extension. Except that it's, I say one thing, if you want to apply, if you have heard the lectures by Romain Dujardin, and if you want to apply equidistribution in such examples, it's absolutely necessary that you have this extension of U1, because then the metrics are usually not smooth, and the curvature form is not strictly positive. So it's really U1 theorem that you have to apply, even if you are at complex numbers. So it's a very important generalization. Okay, let's stop here.